The matter comprising our bodies may have been recycled through countless previous universe cycles, taking different forms in each cosmic epoch. Critics of loop quantum gravity point to the theory's incomplete status and the significant mathematical challenges in fully developing its formalism. Some physicists question whether the simplifications used in applying LQG to cosmology zero-point energy, crucial the mathematics that can alter the bounce dynamics. Those simplified models of cosmic bounces may be missing something essential about the nature of nothingness itself. At absolute zero temperature, when all thermal energy should vanish, quantum systems still pulse with an irreducible energy that defies classical intuition, and this mathematical anomaly might hold the key to what existed before a universe began. When we think about emptiness, we typically imagine a void completely devoid of particles, energy, or anything physical. Yet quantum physics reveals a profoundly different picture. Zero-point energy represents the minimum energy a quantum system can possess, even when cooled to absolute zero where all thermal motion ceases. This is a fundamental property embedded in the mathematical framework of quantum field theory. The equations reveal something startling. What we perceive as empty space contains an extraordinary amount of this irreducible energy. Unlike ordinary forms of energy that manifest as particles or waves, zero-point energy permeates the quantum vacuum as a constant background state. It exists as a permanent feature of reality itself, persisting even when every particle has been removed from a system. This creates one of the most perplexing paradoxes in modern physics. According to quantum field theory, the energy density of the quantum vacuum should be unimaginably vast. Theoretical calculations place it around 10 to the power of 113 joules per cubic meter, a number so enormous it defies comprehension. With such concentrated energy, space itself should be torn apart instantly, or the universe should collapse under its own gravitational weight. Yet when astronomers measure the actual energy density of empty space through cosmological observations, they find a value that's smaller by approximately 120 orders of magnitude. This discrepancy represents the largest numerical error in all of science, what physicists call the vacuum catastrophe. This enormous gap between prediction and reality directly challenges our understanding of cosmic origins, suggesting we're missing something fundamental about the nature of nothingness itself. The vacuum catastrophe intersects directly with our search for pre-Big Bang conditions. If the quantum vacuum contains this intrinsic energy, then perhaps nothing never truly existed. Instead, what preceded our universe might have been a state of quantum potentiality, not empty in any conventional sense, but pregnant with mathematical possibility. The quantum vacuum behaves like a hidden orchestra playing an unseen symphony. Even in its lowest energy state, quantum fields undergo ceaseless fluctuations, manifesting as electromagnetic waves and virtual particles that continuously emerge and recede. Though we cannot hear this cosmic music directly, its vibrations shape the very fabric of reality. What makes these fluctuations mathematically inevitable is the non-commutation of quantized electromagnetic fields, a property where the order of mathematical operations matters. In simpler terms, when you multiply quantities in quantum physics, the sequence changes the result, unlike in everyday math. When fields don't commute, their average values might vanish in the quantum vacuum, but their variances never do. This variance in field strength creates the vacuum fluctuations that give rise to virtual particles. These mathematical properties have measurable consequences. Scientists have attempted to observe light scattering, first proposed by physicist O. Halpern in 1933. Classical physics doesn't allow light beams to interact directly, but quantum electrodynamics predicts they can, a purely quantum effect arising from vacuum fluctuations. Werner Heisenberg and Hans Heinrich Euler developed the theoretical foundation for this interaction in 1936. Their calculations showed that the interaction between two light beams would be significantly stronger when their electric fields are oriented perpendicular to each other. This prediction offers a testable signature of quantum vacuum effects that scientists continue pursuing today. Another fascinating connection links zero-point energy to dark energy, the mysterious force driving the universe's accelerating expansion. Some cosmologists propose that a tiny fraction of the quantum vacuum's energy manifests as the cosmological constant that propels this acceleration, suggesting the same mathematical framework governs both microscopic quantum fluctuations and the largest scale behavior of our universe. The mathematics of the quantum vacuum also suggests a provocative origin scenario. The equations allow for rare but significant fluctuations that could create regions of extreme energy concentration. Through quantum tunneling, these fluctuations might overcome energy barriers that would be insurmountable in classical physics. Recent advances have allowed scientists to experimentally model similar processes, using a 5,564-qubit quantum annealer. Researchers have simulated vacuum bubbles, analogous to liquid bubbles forming in water vapor cooled below its dew point. These simulations provide insights into how a quantum vacuum could undergo dramatic transitions, potentially triggering the birth of a universe. This framework points toward a profound conclusion. The pre-universe state might not have been true nothingness, but rather a quantum vacuum containing all the energy and information needed to spawn our cosmos. The equations suggest the mathematical properties of the quantum vacuum itself contain the seeds of everything we observe today. Resolving the vacuum catastrophe could revolutionize our understanding of cosmic origins. It might reveal precisely how a quantum vacuum could give rise to a universe like ours without violating conservation laws or requiring intervention from outside the system. Scientists continue developing experimental techniques to probe deeper into this quantum realm. The long-sought observation of light scattering would provide additional confirmation of quantum vacuum dynamics. Experiments studying the quantum vacuum aim to detect these fleeting virtual particles and potentially manipulate them, offering insights into the pre-universe state. Beyond physics, philosophical implications. As physicists develop increasingly sophisticated methods to manipulate virtual particles, they inadvertently confront a question that transcends laboratory experiments. Why does anything exist at all? This seemingly simple inquiry has puzzled humanity's greatest minds for millennia and might ultimately reveal more about our consciousness than about cosmic origins. Our journey through the quantum vacuum, multiverse theories, and loop quantum cosmology has taken us to the frontier of scientific understanding. At this boundary, science and philosophy become inseparable companions. When we ask what existed before the Big Bang, we're entering a realm where empirical investigation reaches its fundamental limits. The question, why is there something rather than nothing, stands as perhaps the most profound philosophical problem related to cosmic origins. It stretches beyond mathematical formulations of quantum fluctuations or geometric structures of space-time. Various intellectual traditions have approached this question differently, some remaining within physics, others venturing into metaphysical territory. Scientific approaches seek explanations through natural mechanisms. The multiverse concept suggests our universe represents one bubble in an infinite cosmic foam, while cyclical models propose endless expansion and contraction cycles. These frameworks attempt to provide naturalistic accounts of how our universe emerged, yet they ultimately shift the question rather than resolving it. If our universe sprouted from a parent universe or resulted from brain collisions, we're left asking about the origin of those preceding states. The challenge becomes apparent when we consider that physics has yet to discover a confirmed instance of true nothingness transforming into something. Even quantum vacuum fluctuations occur within an existing framework of physical laws and fields, not absolute nothingness. This observation has led philosophers to argue that complete non-existence may be a logical impossibility, suggesting that some form of existence might be necessary rather than contingent. These considerations connect to the simulation hypothesis, a thought experiment that reimagines ancient questions about reality's nature. Proposed by philosopher Nick Bostrom in 2003. This hypothesis suggests that what we experience as reality might be an artificial construction within a higher-level reality. The argument proposes that advanced civilizations could create detailed simulations of their ancestral past, potentially generating simulated realities that outnumber any base reality. The simulation hypothesis forces us to consider questions about consciousness and existence that mirror our everyday wonder about reality. If our universe were simulated, would the Big Bang represent the moment our program was initiated? These questions echo ancient philosophical inquiries about whether reality exists independently of mind or perception. The anthropic principle offers another perspective on cosmic origins. This principle observes that our universe's physical properties appear calibrated for life's emergence. Constants like the strength of gravity exist within narrow ranges that permit complex structures to form. The weak anthropic principle states that we shouldn't be surprised to find ourselves in a universe compatible with our existence. We couldn't exist to observe an incompatible one. The strong anthropic principle makes a bolder claim, that the universe must possess properties allowing life to develop. This perspective has various interpretations, from suggesting multiple universes with different properties to proposing arguments about cosmic purpose. The anthropic principle reminds us that our observations of the universe connect inescapably to our existence as observers. Religious and philosophical traditions have offered frameworks for understanding ultimate origins beyond physics. Western philosophical traditions often invoke concepts like necessary beings or first causes, while Eastern philosophical systems frequently embrace cyclical models of reality without absolute beginning or end. These diverse approaches highlight a crucial insight. The question of cosmic origins leads us beyond the realm where empirical science alone can guide us. Scientific methodology excels at describing how natural processes unfold within our universe. Yet when we ask about the absolute origin of everything, including space, time, and physical laws, we approach territory where observation and experimentation face intrinsic limitations. As physicist Will Kinney notes in An Infinity of Worlds, if cosmic inflation correctly describes what happened before the Big Bang, it may push the ultimate answer about our origins beyond science's reach. We don't know anything about what came before inflation. It's doubtful that we'll ever know. This recognition acknowledges fundamental epistemological boundaries rather than scientific failure. These limitations are conceptual, not merely technological. How could we empirically investigate conditions before space-time existed? What experiment could probe a state where our physical laws hadn't yet emerged? Some aspects of the pre-Big Bang condition might be fundamentally unobservable in principle. The intersection of cosmology and philosophy raises intriguing questions about consciousness and reality. Some interpretations of quantum mechanics suggest consciousness might play a more fundamental role in reality than classical physics implies. If observation helps determine reality at the quantum level, consciousness might be woven into the cosmic fabric more deeply than we've recognized. This possibility connects to philosophical traditions that place mind at reality's foundation rather than viewing it as a product of material complexity. While speculative, such perspectives remind us that explaining consciousness remains one of science's greatest unsolved puzzles, and that understanding reality might require accounting for the observer as well as the observed. Our investigation of what preceded the Big Bang ultimately reveals as much about human knowledge as it does about cosmic origins. The question may remain beyond complete scientific resolution because we've encountered boundaries where empirical investigation meets fundamental constraints. Some aspects of reality may be inherently unobservable, leaving space for philosophical approaches to complement scientific inquiry. This highlights how the quest for ultimate origins drives us to integrate multiple forms of knowledge as we grapple with existence's most profound mysteries. And here we find ourselves at the frontier of knowledge itself. Our journey through pre-Big Bang theories reveals how science continuously transforms our understanding of reality. This exploration mirrors humanity's fundamental nature, our relentless curiosity pushing against boundaries of what can be known. The quest continues because the ultimate origin question exists at the intersection of empirical observation, mathematical modeling, and philosophical inquiry. As quantum simulations and theoretical frameworks develop, we inch closer to understanding cosmic origins and our place within this astonishing universe. The universe is under no obligation to make sense to us, yet our pursuit of these profound mysteries remains